Yeah, go team. But slopes, how does slopes show up in calculus? Minefields, a field full of mines. Slope fields, a field full of slopes. But where do slopes come from in calculus? Yeah, derivatives, because derivatives give us slopes of tangent lines. And so yesterday, we actually got a little bit further than period 6. Go team. Because we were able to not only get all the way up to this example, but also take some notes on the way. So let me go ahead and actually put these two side by side. I don't think I actually got you guys taking this page, right? Okay. Okay, just the yellow box. Let me do a page with the yellow box. I know you guys can't necessarily see the yellow box. I know it's way too small up here, but you already wrote it down. And let's go through what I did to make that slope field. Now, first of all, did you guys notice on, okay, hold it up. Well, Ruth, I won't touch yours. On this one, do you notice there are a lot of blank slope fields? How are you going to get the baby tangents in order to make a field? By doing what I did yesterday, which was figuring out which points are shown and then plugging in those points. Now, hold on, wait a minute. This is let's see, 4 rows and 3 columns. There were 12 points here. How come I only plugged in 3? Does anybody remember how I did this so fast yesterday? Yeah, if you guys look at sheet number 1 and 4 should be pretty fast to do also. How come? Both 1 and 4 are only dependent on the x values. This is actually a trick or a hint or a clue that's going to be helpful with slope fields. I'll actually have you write down some of those tricks, hints, clues when we get there. But what's really nice is on your worksheet right now, this is due after the weekend. This one's due on Monday. The book homework is due earlier. It's due tomorrow. But on numbers 1 and 4, do you guys see how the derivatives are only in terms of x also? So what can we say about any time the differential equation is only in terms of x and we're making a slope field? The slopes are going to be parallel or are going to be the same for any x value, which means they're going to be the same in vertical lines, right? So anywhere x equals -1, once I did -1, 0, and 1 in the sense of -1, -1, 0, -1, 1, -1. Once I did those 3, I was able just to copy them all the way up because the y values didn't have any difference or didn't make any difference. So I could have done 12 points, but I could have also just done 3 and realized, oh, hey, it's going to whoosh. Now, hold on. Do you guys see any other equations besides 1 and 4 that might also be easier, but in a different way? If you're peeking at the worksheet real fast. 2 and 5. Yeah, that's it, 2 and 5, because they're only in terms of, if they're only in terms of y, instead of following vertical lines with all the slopes being parallel vertically, what's going to be true if it's in terms of y instead? Yeah, they're going to follow or be parallel horizontally. Why is number 3 and number 6 going to be a little bit harder? You're going to have to find or plug in both the x and the y, so you might have to do more points. Now, it doesn't necessarily mean you have to do all the points. And some of you might realize that you don't necessarily have to make a table. I was showing you what I was doing as far as getting the numbers that I went over here and then did rise over run. We'll do some more examples in the notes packet in just a second. But you could have done this mental math as well in the sense of taking your differential equation, like for instance on number 3 on your worksheet. X plus y. Couldn't you, for instance, I don't know, someone pick a point anywhere randomly. Would you pick 0, 0? Would you pick something on the axis? Would you pick the bottom left, which would be -3, -2? I don't know. 0, 0. That's an easy one. So if you plug in 0, 0, 0 plus 0 is? Do you need to make a table for that? No. But how are you going to put the little baby tangent line at 0, 0 with a slope of 0? Well, just true. So you could go ahead and just keep on going point by point and do mental math. You don't necessarily have to make a table. If you were on an AP exam free response, hopefully you'd make at least somewhat of a table, but the nice thing is they don't give you this many points on a free response. They literally would probably not even give you this many. They would probably give you about 9 points. So either like this section or that section is what I've seen them give you before. But the long story short, this yellow box, does it now make sense? For every point in the domain of f, not literally every point, you don't have time to graph infinitely many baby slopes. But for every point that's shown to you with a little point actually shown, the little dot actually shown. Assign a small piece of a tangent line, a baby tangent, with a slope of, okay, plug into the differential equation, whether with x's or with y's or with x's and y's. The slope field at that point will be a baby piece of a tangent with a slope defined by the differential equation, tangent to a curve that passes through. And so I went ahead and said, okay, given this general field of slopes, what if they gave you some sort of initial value or some sort of clue of 0, 1/2? I said it yesterday, but I didn't actually write it. And if you were supposed to sketch the particular solution, this is where a few kids get confused. The slope field, they want to like connect. They want to do like connect the dots. And they're like, yay, like we'll go here, and then it has to connect to there, and then it has to connect to there, and then it has to. Now remember, this is supposed to be a curve, right? So did you see me like literally connecting? No. What was the wording that I used yesterday with particular solutions? Follow the flow. It doesn't have to perfectly connect. You don't literally have to, because remember, there are infinitely many slopes around here. We just did a few indicative ones. So I was like, I don't know. Okay, well, I see when it passes this vertical line, it has to have this slope. So I tried to make it have like that kind of slope when it got there. I knew when it came here, it had to go flat because all of these, it goes flat. And I knew up here, somehow it has to go positive. So I followed the flow. Now, if we got even more slopes like all around here, maybe we're going by halves instead of going by ones, it might be easier to do, but you don't literally have to go connecting the dots. Literally just try to follow the flow to show the general idea. Does that kind of make sense? It doesn't have to perfectly connect all of those different little baby slopes. Okay, so what I didn't have you write down yesterday was this page that somewhat tries to put in manageable steps how to form a slope field. Some of you literally might not need this. The yellow box and this one example might be enough. But here's literally what I did. What I did is make a table solving for slopes, dy dx values, at particular points. Which particular points? I don't know. Whichever ones are shown. Whichever ones are asked for. Sketch baby tangents with the appropriate slope. So you have to plug into dy dx. You have to figure out the slope. And then you have to, in a sense, approximate rise over run without actually showing like up 2 over 3. You have to realize, like imagine going up 2 over 3. Imagine coming back and do a little whoop, whoop, a little sliver of that line. It's going to be approximate. But positive 2 over 3 will be a much, 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 much different slant than negative 5. If given an initial condition, which is what you saw me on the other side do in blue, there was a point that was supposed to be marked 0, 1/2. Sketch the particular solution by following the flow. Once you guys are ready, in your notes packet, guys, in the notes packet, there's a lot of good stuff if you need further clarification or further detail. Our book is bad, but I don't think it goes in as much detail as I would like. It does give you a quick example of a wind pattern, a wind map that actually does look like a slope field, a very, very complicated one. Because if you guys notice, in the sense of mathematically speaking, it's not like just vertical translations of the exact same thing. Depending on where you are, the movement is very different. This could be the example of they're measuring how fast the wind is going and what direction it's headed. But trying to get an antiderivative would be ridiculous. Map out all the different vectors in a sense. Then they can follow the flow to see where the wind is going. That's kind of cool as far as weather applying to calculus. It does talk through some of the different things as far as what we're saying as far as making a slope field, but we're going to pop to example number 2. If you guys have your worksheet close, if you get example number 2 done, maybe you could go look in the worksheet at one that's very, very, very similar. So I think we just saw one that looked like this guy. No, it doesn't. This one says y prime equals. In the worksheet, doesn't it say dy dx equals? Wait. But dy dx and y prime, aren't they the exact same? Yeah. Some of you might be like, okay, it says make a table. I'm going to make a table. Why? That way it'll keep you honest. Okay, it's not totally bad. But some of you are like, I can keep track of numbers in my head like I'm in calculus. Okay, and keep track of numbers in your head. But some way, somehow, we need to get, oh no, slopes put into our field. So I think we just did this one a second ago. We meaning you and I. And I asked you guys, I think I was literally on this problem, right? Number 3 on the worksheet. And you guys said 0, 0. And I was like, yep, okay, plug in 0, 0, and you get a flat line of 0. If I plug in 1, 0, it's going to be a slope of 1, which is up 1 over 1. I pretend I'm connecting. 2, 0, it's like I have a slope of up 2 over 1. Might not be perfect, but the long story short is if I was to connect, remember, I'm just doing a slope there. I'm not doing the dotted. I'm leaving that off. But you or anyone looking at this should see it getting steeper. Now it starts to get a little hard at 3, 0 because it should be up 3 over 1, but you can visualize, we're kind of pretending anyway, right? It's going to be even steeper. If I was to do negative 1, 0, remember I'm plugging into a differential equation. I'm just doing quick mental math. Negative 1 plus 0 is negative 1, down 1 over 1. Your negative slopes, positive slopes, different, right? Same thing with flat slopes. Negative 2, 0, adding is 2, down 2 over 1. Remember, imagine like you're connecting. Some of you are realizing down 3 over 1. Well, that's great. I just did one line. Still 4 more lines to go. Let's do this. It's not horizontal. We can't do vertical because 1, 1. 1 plus 1 is 2, so I have to go up 2 over 1. Oh, hey, he was up 2 over 1. Interesting. 0, 1, if I add, is 1, up 1 over 1. Oh, he was up 1 over 1. Huh. If I go negative 1, 1, that's 0. He was 0. Hey, do we have any patterns? Guess what happens if we keep doing that? What's negative 2 plus 2? 0. What's 1 negative 1? 0. What's 2 negative 2? 0. Why does this make sense? Does anybody see that the zeros are going to happen anytime y equals negative x? And isn't y equal negative x a diagonal line? Sometimes there are patterns. If you have x's and y's in an equation, it might not be horizontal or vertical. It might be diagonal. No, that's not every time you have x's and y's. Number 5. What's the other weird one with x and y? Yeah, if it's not a 6, thanks. If it's not an addition or subtraction, it's not going to follow diagonal lines. It's going to be its own beast. But that's also why it's number 6. It's a harder one. But if you guys notice a pattern, the nice thing is up 1 over 1. Sweet, up 1 over 1. Sweet, up 1 over 1. Up 2 over 2. Up 3 over 3. If you notice, this one's going to be up 4. And then it starts to get kind of like harder and harder to see the difference. Because to some extent, with some grid like this, up 4 over 1, up 5 over 1, up 10 over 1, what happens to these lines? They get closer and closer and closer and closer to being vertical. And to some extent, it's kind of like, okay, I get it. It's getting steeper. I'll do the best I can. Over here with the negatives, let's see. I have negative 1. Then I have negative 2. Oops, that's way too negative. Lo siento. Down 2 over 1, down 2 over 1. Down 3 over 1, down 4 over 1. You guys kind of get the flow? I found patterns and I used those patterns. Could I have made a table with, oh dear, what did we have? 1, 2, 3, 4, 5 rows and 1, 2, 3, 4, 5, 7? 35 different points? I suppose you could have, literally. Would you have wanted to? Not necessarily. But wait a minute, why aren't we done? If we were in the worksheet right now, we'd be done. But we're in the notes packet, and what else does it give us besides just a differential equation? Okay, it gives us an initial value. So we can go ahead and go in a different color. We have a clue. We're going to graph 0, 1. This is where people get confused. How do you follow the flow? What's going to happen as we go to the right? What's happening at this point? My particular solution is going up. Yeah, somehow it's increasing, right? And it's not just going up, it's also going up at a quicker rate, true? So some of you are like, how do I get from there to where I'm going? Just follow the flow. Wind, right? Look at the wind pattern on the note packet. Just follow the flow. Where's the wind going? Oh, it's going that way. Okay, cool. There's the flow. Follow the flow. It gets hard the other direction, though. But as we pass through this diagonal line of horizontals, guess what this graph has to do as it passes through this diagonal line? Has to level off. Good. Okay. Wherever this passes through this diagonal line, it's going to have to level off and have a slope of 0, just like all of these have slopes of zeros. Now it gets weird. How do you go negative? Is there like a weird something? No. That's not following the flow. That's doing something. When differential equations get harder, specifically when you have x's and y's mixed up, it's not just in terms of x, it's not just in terms of y. It's not going to be a simple, super basic one like we saw yesterday with this cubic one. I could solve this differential equation. I could solve it pretty quickly. I know it's going to be 1/3 x cubed plus c. Yesterday I told you guys this is an example of a basic solution to a differential equation. All of them look exactly the same. They're just vertically translated. So, okay, maybe it shifts up, maybe it shifts down, but they all look the exact same. But a more complicated differential equation has much more complicated particular solutions. Go look again at the wind pattern. Go look again at the wind pattern. If you're in Syria and following a much different flow than if you were in Iraq, than if you were in Iran, than if you were in Saudi Arabia, if you pick different particular solutions, you could be going a very different direction. It's not all the same no matter where you are, just with the vertical translation. This one, ironically, I know it's weird, to follow the flow would probably be like this. This would probably be some sort of slanty asymptote. Because if you notice, on one side it's swooping like this, and on the other side it's swooping like that. Does that kind of make sense? So we go to the point that they give us, we follow the flow, and we say, we don't know what's going on over there, so we're done. Just like if I was to put you in a particular country and have you follow the flow, it's going to look very different than if I was to put you in a different country on the wind map. Does that make sense, kind of? Okay. And it's all because this differential equation is way harder to solve. And to be honest, at our level of calculus, we can't solve this one. The addition, there's no way to split that up to get times dx and times dy legally. But we haven't really talked about that yet, so we'll move on. We'll move on. So example 3, you guys busted out real fast. Why real fast? There are only 9 points. There are only 9 points. You guys practice without me explaining it. Get a slope field. You don't even have to, oh yeah, it says sketch a solution curve through the origin. 9 points. Ready, set, go. It's up to you. You can make a table, or you can put your pencil on a point. Think of the x, think of the y. Plug in to your differential equation. Get a number, and then think, okay, if that's my rise over run, where would I be going? How many of you guys have the slope field yet? Okay, talk to your groups real quick, collaborate. What are people doing? What's working? What's not working? Because you should have had one by now if you knew what was going on. It's okay. If you guys have a chance, check out mine and see if you agree. Check out my slope field. I have it done. It's up at the front. See if you agree. Now you guys should be thinking about sketching the particular solution, right? Because they give you a point. Oh, they don't give you like an XY, but they say in words the origin. So how would you follow the flow? How easy is following the flow on this one? Not very. Why? You only had a few points. Now, I get that it took some time to make the few points, but it's a little rough. It was a lot easier when we were over here, right? Because we had more points to be able to follow the flow. So if we were to go ahead and do something like, oh, my computer's not working. Let's see. Let's see if Wolfram does this very well. So if you guys are noticing, there's a very particular way of approaching slope fields that should be, theoretically, if you knew how to program a computer, fairly easy to make a computer do. You could program it fairly quickly in a calculator if you understood programming language, because you're pretty much just plugging into an equation. Let's see, find the slope field. I'm actually not sure if Wolfram does slope fields. Plus y squared minus 1, is that your differential equation? And I'll do dy dx. It's a bit more technical than y prime. Let's see. There we go. Yeah, super weird, right? Let's see if I can do more points. So it's weird because our 0, 0 would be right here in the middle, right? And they gave us a little bit of negatives on the y's, a little bit of negatives on the x's. They didn't show like our coordinate plane. But if you followed the flow, it seems like it would have some sort of, right? Some sort of curvature like this. So then coming back to ours, a quick thing with slope fields. I can tell right here that it's horizontal. So somehow it's going to have to go horizontal. Somehow it's going to have to go horizontal. And I'm not exactly sure what else it's doing, so I'm going to be like, yay, we're done. Technically, you could probably see that somehow it needs to go negative right around here. So you could even have it like going negative and then going positive right around here. You could have it going positive, but that was a weird one. So the fewer points you have, the faster it is to make the lower idea, or the harder it is to follow the flow. But if you guys notice, once again, if this is meant to, if I come back here, if this is meant to at the very beginning, visualize solutions to differential equations, specifically of very, very complicated ones like the wind map that you saw. Maybe algebraically we couldn't solve for an actual equation of the particular, but if we can follow the flow, and that'd be using some technology, using some computers like you just saw Wolfram Alpha do, right? It was able to make me what I needed to see so I could see the behavior of the original without actually solving for it. Ryan, go ahead.
When there is a flat line, there'd be a vertex of a concavity
Yeah.
around that point.
But remember, we're not just like connecting the dots. So we have to follow the flow. We have to decrease. And so then I assumed, thinking about this diagonal line, I was like, okay, well, I have a flat here. So when it crosses through this diagonal, I'm going to have it flatten out. See it? And then from here to here, I'm going to have it flatten out. So I have it flat here, thinking maybe it's going parallel this way. Looking at Wolfram, it kind of seems, to have all these flat that are kind of going around. So you would kind of somehow flatten out, and then you would somehow flatten out. But remember, we don't have to connect the dots. We don't have to like go up and then flatten or go over and then flatten. We have to follow the flow and try to flatten somehow in a way that seems to be consistent. I know it's kind of weird how to follow the flow without connecting the dots. Kiddos, example 4, example 5. What changes? This is much more AP-ish. If they actually want you to draw a slope field, it'll show up in the FRQs and it'll be a part A, and there'll be a nice little dot grid system. Otherwise, there's no time that you'll be actually drawing a slope field. What's going to be instead? Multiple choice. So what do you guys see up here? You have 2 slope fields, 1 and 2, and you have lots of different options, 1, 2, 3, 4, 5, 6, 7, 8. 8 different possible functions. What's most important, and we'll write down some clues, what's most important with matching problems in slope fields is getting oriented correctly with what you're matching. Because when you were looking over here, y prime, this differential equation, dy dx, actually determined the slopes. The flow indicated or showed, but I guess I don't need to type that, showed the y. dy dx got us the actual tilting of the slopes in the points. Y flows through. So when you guys are matching these slope fields to y's, all you're trying to figure out is, okay, who flows this one, and who flows through that one. This is probably the easiest one. I think this is the easiest one. If you guys follow the flow, who does this look like, just in general? Some sort of trig function, and if it starts at the origin, right? Yeah, that's going to be a sign, so F goes with number 1. Totally agree. Why? Because we were looking at, since all of these are y's, we were looking at the flow. Does that make sense? So who flows like that? Nope, nope, nope. Ooh, how's he look? He's a cubic. He has a 1/6. I don't care, whatever. He got squished or stretched or something, but he's a cubic. Does anybody else seem to have that? We already found him. There's no other like him. That's a weird like him. And that's a, hey, basic graphs at their finest. Go team. Follow the flow. So then you guys think about number 5. We're in the note packet. Did you get one of these, Nick? Yeah, okay. Remember, if you're bored, you can totally be in the worksheet. You can be playing with similar types of problems, being like, hey, I know it's homework. But your focus tonight, grading the integration is net change. If you didn't get to last night, I apologize again. But then the book work. You have a few days to work on the worksheet. What do you guys think? Who seems to follow the flow the best? ln. Why? It doesn't seem to be cosine. I don't see any, right? E to the x is a swoop up. E to the negative x inside is a horizontal flip. Nope. X squared? Nope. He's the only one. Oh, yeah. Makes sense? Now, pause, get oriented. What's different in number 6? You don't have the y's anymore. You're not following the flow anymore. What are you doing instead? Thinking about the, oh, you can't even see it. Yeah, slopes. Now, that doesn't mean you can't think about the flow at all. Maybe you can think about some of the flow. But if you think about some of the flow, you're going to have to think about, hold on, where could this dy dx have come from? Oh, wait, I can do him. Where would that dy dx have come from, guys? Wouldn't it have just been e to the x? Who else do I... Uh-oh, I better not do the ones with x. Where would he come from? Come from, meaning anti-derive, meaning go back to y. If you anti-derive x, move dx to the other side, integrate both sides. Wouldn't he be like a 1/2 x squared? Maybe with constants, but where would he have come from? I can follow the flow on 3 of them, and I only have 3 left to think about. Okay. Anybody see an e to the x-ish one? F. See the swoop? The exponential swoop? There he is. Okay, so that's my letter I. Anybody see a 1/2 x squared? An x squared, a parabola. B. Yeah. So we have this one, done. We have this one, done. It's going to be Roman numeral 4. Anybody see a negative cosine? Yeah. We like these ones. They're kind of easy to pick out. Okay. We've gotten rid of 3. We have 3 left. Why am I going to draw your attention to number 3 and making him match next? There's only one variable. It's only a y. So I know there has to be parallel slopes in what direction? Vertically or horizontally? Horizontally, because it's dependent on y. Y equals is a horizontal line. What's the only one up here that has all same slopes horizontally? So I have this one down. Now we have a little bit of a debate. Unless you remembered my trick from a second ago of diagonal slopes and what kinds of differential equations they always come from. You guys see the diagonal slope one? Isn't it e? What kind of differential equation could get me lots of zeros in a diagonal way? 0 minus 0, 1 minus 1, 2 minus 2, 3 minus 3. What are all of those going to have in common? Flat slopes. This guy is going to go in a diagonal fashion. If you had a colored pen, there are things like, hey, plus or minus moves diagonally. Hey, easy ones in terms of x, maybe I can anti-derive, follow the flow. Hey, in terms of y, going horizontally. So then that leaves us with letter C being number 2. We were actually quite lucky on this one because they are so different. Sometimes they all look like this, but with negatives in different spots. Ugh, that one's messy. But if you guys notice, for this one, if x equals 0, you're going to have horizontal. And if y equals 0, you're going to have vertical. If x equals 0, the whole thing is 0. The slope is flat. If y equals 0, undefined, infinite. Like, right? Remember? Skiing flat, skiing, dying. Okay. So up here, when y equals 0, oh, it looks to be, right? If you were to follow the flow, it looks to be vertical there. And then x equals 0, flow. Yeah. So even though the programming, the graphing calculator or whatever utility they used, didn't quite show, well, it kind of shows up and down. Doesn't really show flat so well, but if you follow the flow, that would have to go flat when x equals 0. That's a good hint for those fractiony ones. But we have to get harder than that. Wrong way, sorry. Let's go example 7, and then we'll go back to tricks. Because I want to go harder before I tell you tricks. Because right now you're like, what? This isn't too bad. Hopefully. Hopefully. Although maybe this one wouldn't be too bad either. Let me freeze the screen. You guys try to make the matches. These are still pretty different. The nasty matching might be in the slope field where they're super, super similar. As you guys are playing with those, if you do finish early, you can go ahead and go look at your worksheet and see if there are any matching ones. Be careful to orient yourself. Are you just following the flow? Are they all y equals? Are you just following the flow? Are they all y equals? Or do you actually have to look at the slopes, the dy dx equals? As you're trying to solve, I'm putting up my version of some clues as far as how to summarize some of these things that I've been doing. There is this whole by calc, you could actually download like a TI graphing program. But remember how I said they would not put these on a graphing portion of the test? So I don't know if it's necessarily all that helpful for me to get it on your graphing calculator. Instead, I would say you can always pull up Wolfram Alpha if you need to check out more detail in the slope field, like in a homework or something. With different types of problems they'll give you. I'm just going to go through and write out a few hints as you guys are trying a few more multiple choice. If you run out of them in the note packet, go peek over in the worksheet. And we'll check the answers that you got in a second. There are some hints. You guys can take a picture of it if you want. You can just kind of ponder it for a bit if you want. The ways they can give you questions, basically, you just need to figure out, is it a y or is it a dy, dx? Is it a flow or is it actually slopes? Now, if it gives you a differential equation, one more time, if you can think backwards anti-deriving, if it's in terms of x, then maybe you could go from slopes to flow, and that might help just a little bit. Over here, I've summarized just a few of the different lookouts that we were using that I was trying to verbalize. If you can see in a field some flat lines, where is that happening? First, second quadrant, horizontal lines, vertical lines, diagonal lines. Sometimes it's fairly easy to pick out the flat lines and be like, okay, well, at these places the slope is 0. Which equation would get me there? If you have slopes along the x-axis, you can think of, okay, when y is 0, this has to happen. Maybe it's all the same, maybe it's always changing, but you can think of plugging into your differential equation y is 0. Okay. Or along the y-axis, can I tell if I plug in x is 0? Does that determine anything? We already talked about if the differential equation only has x's, the slopes will be parallel vertically, like x equals lines. If they're only dependent on y, slopes will be parallel horizontally. And then if worse comes to worse and nothing else is working, I have one particular multiple choice question in my head where nothing would get you to the match that you need. You can always go to a particular quadrant. You can always say, okay, if I plug in 2, 2, 3, 3, if I plug in -1, 5, is it matching with what I see when I plug into the differential equation? You can either test points, like actual individual points, because maybe one quadrant, maybe the first quadrant has negatives and flats and positives. You can't just test one point. You have to test multiple. Sometimes testing a quadrant is good enough because the whole quadrant's positive or the whole quadrant's negative, and that only works for one or the other. But sometimes you have to test points as well. So when you guys were making matches, or trying to make matches on example number 7, I'll end class going back to those 2 pages I just had. So you can take a picture of it if you didn't get one yet. When you had to make all these match, were you guys able to figure out that C should have gone with number, ¿dónde está? B. Sorry, Roman numeral 1 should have gone with B. Roman numeral 2 should have gone with C. Roman numeral 4 should have gone with the diagonal. And Roman numeral 3. What? Okay, work on the bookwork slope fields. If you have time, work on the worksheet. Let me get those 2 clue pages up if you want a picture on the way out, and I'll see you guys later. Bookwork, due Google Classroom tomorrow. Bye, guys. If you haven't graded yet, it's all up in Google Classroom, ready for you to access. Oh, it's propping open the door. Level off is like going horizontal. So it could be going horizontal this way or that way.